Hello, good evening, everyone. Okay, so welcome to today's lecture. All right, so over the past, I think week, I received quite a few queries regarding the assignment and the project. Okay, so I think assignment mostly it should be done. Okay, so later I'll just talk a bit more of the sorry, not project, the term paper. All right. Yeah. So in today's class, we are going to be starting on the new chapter on multi-threaded programming. If you look at the slides, okay, so I uploaded it just now. Okay, so actually I thought I uploaded over the weekend, but I think I forgot. All right, so I uploaded it just now, and it's quite a comprehensive set of slides. Okay, because everything is inside. Okay, so today we will cover sort of part of it. Okay, up to a certain point, and after that I'll switch over to do some demo using the software. Okay, so if you haven't installed the software yet, please start looking at it. All right, and I'll also talk a bit about the software installation and some issues that you may face and how to overcome that. Okay, so let's get started with the lecture. Okay, on multi-threaded programming. Okay. Okay, so in multi-threaded programming, we are going to be looking at all the various aspects of multi-threaded programming in this lecture, as well as things like data protection. And another thing is also how different threads or different tasks can actually communicate with each other. So we're going to talk about a few different aspects of multi-threaded programming. And why RTOS or why OS in general, I would say, is something we discussed last lesson. Right, so towards the last part of the previous lecture, we talk about this example of a robotic car, okay, that you want to control, okay, and when you think of it at a very simple approach, with a simple approach, you can definitely do it with what you already know, which is writing a loop and doing some checks and so on. Okay, but when the complexity of the system goes up, okay, so let's say I add a sensor, I add a LiDAR, okay, to scan, then I want to add some Bluetooth connectivity or add some Wi-Fi connectivity. Okay, so when I scale a product or a project, okay, with more and more features, okay, then the traditional way of thinking, which is having a big sort of super loop, okay, and doing task one, writing everything in the loop, okay, so while one loop, and then I say do task one, task two, task three sequentially, it's not going to work. Okay, once the complexity grows beyond a certain point. Okay, and of course, another critical factor is the responsiveness of the system. Correct, because once something changes and I need to insert a new task here, okay, task A inside here, then the whole dynamics changes, correct? Then the time that I take to complete the loop, the time that I take to respond to certain events, everything will change. All right, so that is where moving away from the traditional way of thinking and moving towards this multi-threaded approach is very useful. Okay, so that is something that we sort of discussed, I think, quite in detail last lecture, so I will not repeat that part. Okay, so the whole idea, okay, of multi-threaded programming is you break up a task, okay, into multiple threads. Okay, so again, the terminology again is sort of mixed up over the years. Okay, so when you look at different references, web pages, and so on, you will come across people using the terms thread, okay, task, and process. Okay, and we also talked about this last week. So generally, okay, the common approach to thinking is the process is the higher level sort of activity you want to carry out, and from there you break it up into multiple tasks. Okay, so you can think of the process as the project. That means you want to control the car, you want to perform some operation, and you break it up into multiple tasks. Okay, so these tasks that we write, or these threads that we write, okay, have to be written in a different way compared to how we were thinking in the traditional approach. Okay, so one of the first things that you will see when we look at the code later on is every task that we write, or every thread that we write, in the beginning of that thread, we will do some initialization. Okay, maybe some variables, some settings, and so on. And after that, it actually runs into an infinite loop. Okay, this is something that you don't do normally, right? In a normal situation, when I have a main code here, okay, and I call function A, function B, all right, when I write function-based programming, when I call function A, I expect to do certain things, and I expect to return and carry on. All right, you do not write a while one loop inside function A and get stuck there forever. Okay, so this is something different. Okay, so inside this multi-threaded sort of approach, every thread is actually written, okay, with the code inside an infinite loop. Okay, so of course, if it's an infinite loop, it's supposed to run forever, right? So how is it still able to allow another task to run? Okay, so you need to put in some sort of techniques in place so that even though it is in an infinite loop, I still allow other tasks to run. Okay, and usually what we do is every task has some condition to run. Okay, so it may run, but eventually at some point of time, it may have to wait. Okay, so you might wait for some data, you might wait for some event, all right? And then once that event happens, or once the data is available, then we will be able to carry on from where we left off. Okay, so the idea is, even though it's an infinite loop, okay, it will not be written such that it just keeps running infinitely. You will actually have to wait for some event, okay, or some data to be available before it can continue processing. Okay, the heart of any OS is basically what we call the kernel. Okay, so this kernel is basically the entire library, okay, of all these APIs or routines that we use that actually helps to manage the multi-threaded program. Okay, so depending on which OS you use, okay, so if you write a program for Windows OS or Linux or Android or anything, all right, at the very lowest level, you're actually making use of the OS kernels. All right, it's just a matter of whether the level at which you're writing is higher or lower. All right, so if you're writing at a higher level, then all of this is abstracted for you. Okay, if you're writing at a lower level, okay, like what we're going to be doing, okay, we are actually going to explicitly call these APIs, all right, to make use of the features that the OS provides us. Okay, so what does the OS provide? Okay, so of course, besides creating all these threads, okay, it also has the ability to perform coordination, okay, among threads, synchronize the threads, okay. Maybe one task will run, and after a while, another task must run. Communicate, all right. How can one task send data to another task, and so on. And there's also the concept of priority. Okay, so some tasks will be able to have a higher priority compared to some other tasks. Okay, so even though we have all these different tasks in the system, okay, one of the key things is every thread will run as if it owns the CPU to itself. Okay, so we will write the thread such that it has a specific objective to fulfill. All right, and of course, every thread may have some dependency on others. All right, so even though we write it to run independently, there is some inherent dependency. Okay, and that dependency again depends on the project that we are or what we are trying to achieve. Okay, so for example, if I take the example of a media player, okay, so in the media player example, if I have a task that deals with video data, okay, another task will deal with audio data, so all of them can be written as running independently, but eventually there is still a dependency because I need to make sure my network task that is receiving the data packets is actually running and is able to send the updated information over. Okay, so even though video and audio may be running as separate tasks, the network task still has a overriding synchronization sort of authority. Right? Only when the network data becomes available, then video and audio can play. Okay, so there is always this concept of independency, right? But at the same time, synchronizing with some other tasks. Okay, and of course, the whole idea is how do I partition it into a set of independent threads. Okay, so the whole idea is by going in this multi-threaded direction, we are actually simplifying the entire project by breaking it up into partitions. Okay, so instead of looking at the whole big problem, we say that, okay, now I just write a task that is focused on one particular functionality, then another task, another functionality. And then later on, I can think of how the overall dependency, the communication, the flow is going to be like. Okay, so it's actually a very, very powerful way of programming because instead of looking at the whole objective from a very as a very big requirement, you break it up with very small requirements. I mean, that is something that we still do right now, correct? Whenever you're going to write a software, we still have the idea of divide and conquer, right? We still divide and break it up into functions, and then we call the functions or call the routines and so on. But now the difference is instead of thinking of breaking up into functions and then deciding which function I call first, which function I call next, and so on, you think of them as independent tasks, and then they can sort of interleave among each other depending on how you plan the whole architecture. Okay, so it is something similar to what you have done, but the way in which the overall flow is going to happen is very different. Okay, so in the concept of concurrency, right? So when we say that multiple tasks are running at the same time, okay, eventually we only have one CPU, so only one thread runs at a time. So when one thread is running, again, one thread is running, we say that the others are in a suspended state. So suspended is a general term. Okay, there are more specific terms that we will use depending on why they are suspended. Okay, so we will look at that. And what is happening is the processor actually is switching very fast, okay, between all the various threads. So we have this idea of concurrency. Okay, and the idea of priority is again coming back to the concept of having some threads or some tasks that are more important, okay, than others. Okay, so let's look at the idea of a thread first. So when I create a thread or when I create a task, okay, what am I doing? I'm actually telling the OS that I want to create a special block of code, okay, to do something. So let's say I call this okay, task A. Okay, I call this task A. So when I create task A, I'm going to write some code for this. Similarly, when I create task B, I'm going to have some code for this. Okay, but at the same time, since we know that I'm continuously switching between the tasks, all right, and we need to keep track of what is happening. Besides the space for the code, I also need some other space to store all this additional information about what was I doing, what were the variables that I was using, what was the value inside them and everything. All right. So that is basically what we call the context, the entire context of the task, which includes the what we call the stack and all the registers. Okay. When a processor executes, it makes use of the internal registers. When a processor executes code, we know that the internal registers are used. Okay, so we saw that in the MIPS architecture. In any architecture, it's the same. All right, so while I'm executing a particular task, I'm using some registers, okay, and it has some value. And besides the registers, I may also have some other variables, information in memory. All right, so what I need to do is I need to make sure that all this information is kept securely inside the context of the tasks that once it is created. Okay, so this is all generally what we call the stack space of the task. So when I create a task, I also need to create this additional stack space to hold this information. All right, so when I hold this information, what happens is when I switch in and switch out, I'm always able to recover the exact point and the data from where I left off. Okay, and that is basically what we call the context switching. Okay, so this happens very, very fast. Okay, very, very fast, because there are so many tasks that are running and the OS is constantly switching between these various tasks. Okay, so I need to make sure that if I'm currently running task A, okay, and while I'm executing, there is a need to switch to task B, then A must be saved and B must be restored. Similarly, when I switch back, I save the B context and restore the A context. And all of this includes all the registers, the variables, everything from the stack space of each particular task. Okay. Now, in terms of multitasking, okay, so there are different sort of policies in place on how the OS may deal with multitasking, with the multitasking environment. Okay, so one possible way of dealing with it is what we call a non-preemptive multitasking. So this non-preemptive, another term you might come across that is similar to this is what we call cooperative. So in a cooperative environment, okay, in a cooperative environment, what happens is the task that is running, okay, must voluntarily call what we call a yield function. Okay, that means it must voluntarily give up the CPU, okay, so that another task can take over and run. Okay, so this is the cooperative way. Okay, so OS may have this option, okay, where you can switch to this non-preemptive mode. So the code must be written in a way that the task, any task that is running, must have some ability to voluntarily give up the CPU. Okay, so in this case, what happens is, okay, when the yield occurs, okay, the task that will be scheduled to run, okay, will follow a particular sequence. Okay, so let's look at this. Okay, let's look at this example here. Okay, so there's a question, how do you assign priority? Okay, so we will assign the priority when we create the task. Okay, so that part I will show you later when we're looking at the code. Okay, so when I create the task, okay, I can also assign a priority to the task. Okay, so in this example, okay, so what is happening? All right, so let's look at some general idea first. Okay, so in any OS, all right, at any point of time, okay, so maybe before this slide, let me okay, so let's talk a bit about this overall concept of task state. Okay, so when I first create a task, okay, so let's say I first create a new task. Okay, by default, what happens is it goes into this state called ready. Okay, so when you say a task is ready, okay, it means that it has all the resources it needs and it can actually take control of the CPU and run. Okay, it can take control of the CPU and run. Now, at any point of time, you can have multiple tasks inside this or having this state called ready. Okay, because your system can have 5 tasks, 10 tasks, 100 tasks. Okay, so all of this will be inside what we call a ready queue. Okay, so you can have task 1, task 2, and task 3, and so on. Okay, so of course, this queue also depends on the priority. Okay, it also depends on the priority. So tasks that are having a higher priority will automatically go up the queue. Okay. Now let's assume that right now all these three tasks T1, T2, and T3 that I have are all in the having the same priority. Okay, all having the same priority. Okay. So once I have all these three tasks with the same priority, okay, a decision has to be made on who is going to take over the CPU. So whichever task is taking over the CPU, that task will be considered to be the run state. Okay. So from the ready queue, I need to be able to select one task to switch to the run state. Okay, and that is determined by this manager. All right, and this manager is what we call a scheduler. Okay, so in the OS, okay, within the kernel, there is this sort of code which is called a scheduler code. And what this scheduler does is it will always look at the queue and select the person at the top of the queue to transition. So in our case, what will happen is T1 will get your ability to run and take over the CPU. Okay, so when T1 is running, of course, whoever is in the queue all will move up. Okay, so T2 will come here, T3 will come here, and so on. Okay, so that is the basic concept of how a task is selected to go from ready to run. Okay, so that is a very basic concept. Now, the example we're looking at right now is, okay, when I am running, okay, so when the scheduler selects the highest priority thread that is ready to run, okay, so let's assume that right now I am running. Okay, so after so this is basically a task that is running in the run state. So it do some work, and then after that, I want to call yield. Okay, so if I call yield, so this is equivalent to saying I want to yield. Okay, which is to voluntarily give up the CPU. Okay, if I say no, then I can still continue to be in the run state. Correct. If I don't want to yield, I will still continue to be in the run state. Okay, but if at some point of time I say yield, okay, if I say yield, then what will happen is I'm saying to the scheduler that I want to voluntarily give up the CPU. Okay, I want to voluntarily give up the CPU. Now, when that happens, what happens? What will the scheduler do? It will select the highest priority thread that is ready to run. Okay, if not the current thread is suspended and new thread is resumed. Okay, so let's assume that in this case, okay, if let's say all the three tasks are equal priority, okay, then all of them have an equal chance to run. Okay, so when T1 calls the yield, okay, when T1 calls yield, it will be able to transition back to ready. So when it transition back to ready, you will join the queue. Okay, because right now I'm saying that all three have the same priority. So all of them are in the same queue. Okay, so there is no one that is more important than the other. So when T1 transition back to ready, it joins the queue, then the T2 will get to take over the CPU and run. Okay, and then this process repeats. So when T2 eventually says yield, then T2 will come here. Okay, and then T3 will get a chance. Okay, so this whole process will keep on repeating. Okay, now of course along the way, okay, if there is a higher priority task then that comes in, then that task will always go to the top of the queue. Okay, that task will go to the top of the queue, and once that the current task calls yield, then that task which is the top of the queue will take over the run state. Okay, so this is how a cooperative system works. Okay, but again, as you can see, one of the key drawbacks is this. Okay, I must voluntarily call yield to allow another task to run. Okay, so if your code, okay, in the code, there is no yield function, okay, and the task that is running somehow just hogs the CPU, then your whole system might crash, right? Because then you do not allow any other task to actually take over and run, okay, because you are expecting every task to give everybody else a chance. Okay, so it comes back to issue with the how the code is written for each task. Okay, so that is again one of the drawbacks. And if once it is a non-preemptive system, you also are not able to ensure some timing response for high priority tasks. Okay, because even if I have a high priority task, okay, if I come back to this example, okay, if let's say when T2 is running, suddenly there's another task T4 that is higher priority. So T4 will go to the top of the queue. But even though it is the top of the queue, it cannot take over the CPU until T2 calls the yield function. Okay, so the concept of having a deterministic response time is also not there. Okay, because you still are dependent on the current task voluntarily giving up the CPU. All right, so of course that is one option. Okay, and in some cases maybe that is good enough. Okay, give me a minute. Yeah, so with the non-preemptive approach, okay, you have those challenges. Okay, so that is why, okay, to ensure real-time response, okay, we have this idea of preemptive multitasking. Okay, preemptive multitasking. So what is preemptive multitasking? Okay, so let's come back to the same concept. Okay, of task state. Okay, for preemptive. Okay, so in the preemptive context, okay, the same thing. Okay, so I first create a new task and that task transition to the ready state. Okay, and as before, you can have multiple tasks. Okay, so if I first create task one would be here, and if I create task two and I say both of them, task one and task two, are same priority, then when the scheduler comes in, what will happen? Task one will be selected to go to the run state. Okay, so task one will come first. All right, now if along the way, okay, before task one goes to any other state, let's say I create task 3. Okay, and task 3, okay, let's say this is both considered low priority and this is considered medium priority. Okay, the moment I create task 3 with the medium priority, that task 3 will automatically go to the top of the queue. Okay, and the moment the scheduler sees that there is somebody, that the person who is in the top of the queue is higher priority than the one that is currently running, it will immediately switch out the task 1 and allow task 3 to take over. So it does not wait, okay, it does not wait for a task to give up the CPU. The moment a higher priority task joins the queue, it will immediately perform a context switch. Okay, so whichever task that is currently running will be forced to give up the CPU, and the higher priority task will actually take over. Okay, higher priority task will take over. Okay, so that is the concept of a preemptive scheduling OS. Okay, that means the moment a higher priority task joins the ready queue, that will immediately go to the top of the queue and it will cause the current task. If the current task is a lower priority that is currently running, then that task will be forced to give up the CPU. Okay, so that is the idea of preemptive. Okay, now in this example over here, okay, what we are saying is, if currently I have two tasks, okay, thread A is running, okay, and let's say thread A or task A is considered low priority, and task B is considered medium priority, and currently task B is suspended. Okay, suspended again is a wait state. Okay, we will discuss this in a bit more detail in a while. But for now, when we say suspended, means it is not able to continue because it does not have some resource that is available. Okay, so what do you mean by resource? Okay, so resource, you can think of it as maybe access to some memory, access to some device, okay, or some data that is supposed to be there is not there. So it's supposed that the thread B is supposed to do something, but currently it is not having all the information that it needs, so it cannot continue and perform. Okay, so it is suspended. All right, now let's assume that while task A is running, okay, an interrupt occurs. Okay, so this concept of interrupt we sort of roughly covered. Okay, and it's basically an event that can trigger a code to be executed. Okay, so it could be some data coming in through the network port, could be a button that is pressed, okay, some data through the Bluetooth or something like that. Okay, so now some event occurs and that triggers an interrupt. Okay, and that interrupt, okay, may be the key to releasing some resource that task B was waiting for. Okay, so sometime when the interrupt occurs or something else happens, that may be the thing that the task B was waiting for. Okay, so maybe the data that he was waiting for suddenly came through the network. Okay, or the button that was waiting to be pressed was pressed. Okay, so when that particular resource that task B was waiting for suddenly becomes available, then what happens is the OS will be able to switch the task from a suspended state to the ready state. Okay, so when that happens, okay, when that happens, and since task B is higher priority, what would happen is task B will automatically go to the top of the queue. Okay, so inside the ready queue, there could have been other tasks. Okay, so previously there could have been task C, task D, or whatever. Okay, but the moment task B came available and it because it became unblocked, okay, and it went to the ready state, if the task B is higher priority than whatever is in the queue, then task B may go to the top of the queue. Okay, and since task B is higher priority than task A, then task A will transition to the queue and task B will come to the run state. Okay, so this sort of dynamic behavior, okay, and switching happens continuously. Okay, so we do not know when it will happen. Okay, it happens continuously many times, managed by the OS. All right, so our objective is to focus on the code. Correct. So when you write the task A, when you write the task B, we must be very careful to look at, okay, what are the resources that we need, how are we going to synchronize the different tasks, okay, and make sure that the execution follows in a particular flow. Okay, and if the data is not available, the resource is not available, what can I do? How can I put myself into a wait state? Okay, so these are some of the things that we need to think about when we are designing the overall architecture of the OS-based program. Okay, so right now let's look at one more aspect here. Okay, so right now we said run and ready. Correct, run, go to ready. Okay, so when you are running, okay, that means when the task is making use of the CPU, we say you are in a running state. Okay, when you're not in the running state, okay, because of something else, okay, that means you want some resource but it's not available, then what happens? Okay, So what happens there is you go to another state. Okay, and that other state is what we call the block state. Okay, so again, block is a term that in some books you may see as suspended, okay, or wait state. Okay, so these are all common terms you might see in reference books. So block, suspended, or wait. So there's also a chance while I'm running, I may go to a block state. Okay, so what is a block state? And what's the difference between going to block and going to ready? Okay, so when I go to the block state, okay, it means that I cannot carry on running because I don't have something that I need. Okay, so it is always tied to some resource. Okay, it could be a memory, it could be a hardware, it could be something. All right, so I'm running, but I cannot continue running because I'm blocked. It is just like, for example, when you open up your Zoom, okay, and you want to on your video, and sometimes it says I cannot on the video because another application is using the video. Okay, then you realize that maybe you are doing a video call with on Skype or something else, and you did not turn off the video there. So the Skype is still holding on to the video, so your Zoom cannot on the video. So something like that. Okay, so you are running, but you are unable to proceed because some resource you want is not available. Okay, so in our case, or in that case, okay, you may go to what is called a block state. So when I say block, that means I do not allow the task to continue until that resource becomes available. Okay, so until a point of time when the resource becomes available, then the OS will be notified that the resource is available, and then from the block state, I'll be able to transition to the ready state. Okay, you can never go from block to run. Okay, because who goes to the run, only one person can decide, the scheduler. So only the scheduler has the power to decide who is going to run and take over the CPU. Okay, so when I go to a block state, which means I do not have some of these resources, then when I eventually get the resource, okay, then I will be able to unblock. So the OS will unblock me, but when it unblocks me, it will transition me to the ready state. Okay, when I reach the ready state, it again comes back to the same thing. Okay, depending on my priority, I will be put in the queue. Okay, so if I'm a high priority task, okay, I may go to the top of the queue. If not, I'll go somewhere in between. Okay, depending on my priority level. Okay, so these three states, ready, run, and block, are very important. Okay, because that sort of very much determines the entire flow of the whole system. Okay, so at any point of time, your tasks will always be in these three states only: ready, run, or block. Okay, so when I'm ready, that means I'm in the queue. Okay, queue waiting for my turn. The scheduler will decide, okay, based on the ready queue, who will transition to the run state. Okay, and from the run state, okay, while I'm running, if somebody more important comes to the top of the queue, I will be forced to give up. But when I'm forced to give up, it does not mean that I don't have the resource, correct? I have everything that I need. The only issue is somebody more important came along. So since somebody more important came along, I'm forced to give up the CPU. So in that case, I will transition to the ready state. Okay, I will only go from run to block if I don't have something that I need. So if I don't have something that I need, then I'm forced to go to a block state, and that block state will only be unblocked when the OS sees that the resource that I want is now available to me. Okay, so this transitioning between these three states again is very important because that determines the whole flow of your entire software. Okay, so we will come back to this again and again when we look at all the example code and so on. Okay, so now let's look at some of the challenges. Okay, some of the challenges. Okay, so as a question, is it always one task is higher priority than another? Okay, not necessarily. You can create tasks of equal priority. Okay, you can create tasks of equal priority. Of course, when you create tasks of equal priority, then what happens is when one task is running, okay, it will run until a point of time where it has to go to some block state. Okay, because if you create tasks of equal priority, okay, let's say I create tasks T1, T2, and T3, all of them equal priority. Okay, and task 1 runs first. But if task 1 runs and it never reaches a point, because if you remember just now we said that every task is written as an infinite loop. Okay, every task will be written as an infinite loop. So if inside the infinite loop, I do not make any provision for task 1 to give up the CPU in any way, okay, or go to a block state because it has to wait for some resource, then eventually task 1 will hog the CPU forever. Okay, so we need to make sure that when I write my task, I factor in how some other tasks will also get a chance to run. Okay, so there must be some way, some mechanism in place that makes sure that when task 1 is running, task 2 will also get a chance to run, task 3 will also get a chance to run. Okay, so we need to think about this when we design the software. Okay, so we will get a better idea, okay, later on when we look at the example and the code and we understand how this is going to be achieved. Okay, now let's look at this idea of a shared resource. Okay, and why is this an issue? Okay, so let's imagine that I have one buffer here. Okay, a memory buffer. Okay, so let's assume this is 100 bytes. Okay, and I have task 1 and task 2. Okay, and task 1 is supposed to write, okay, to it the raw data. Okay, task 2 is supposed to read, do some processing of the data, and then after that write back, okay, to this data. I mean, write back to this buffer. Okay, so task 1 is supposed to write the raw data. Task 2 is supposed to read this raw data, process it, and then write it back. Okay, so this is a very common thing, right? Because you may have different tasks designed to do different things with the same data. Okay, so when you have this kind of requirement, okay, what is the key challenge? The key challenge is I need to make sure that when task 1 is reading or updating all these 100 bytes, okay, task 2 should wait until task 1 finishes. Correct. So I need to make sure that when task 2 wants to read and process and write, it should only do when task 1 is finished. Okay, and similarly, task 1 cannot be writing if task 2 is currently in the process of reading and writing. Okay, if not, what will happen? If you imagine that task 1 write halfway, and then before it finish, I switch to task 2, and then task 2 starts from the beginning and start to process the data, and it finishes everything. But what happened? Only the first half of the data was new data. The second half was all the old data. But as far as task 2 is concerned, it thinks that it already processed all the data. Okay, so it is a very common issue, right? Because you have a shared resource that both tasks want to access. Okay, but we need to protect this resource. Okay, we need to protect the resource so that when one task is trying to access it, okay, it should be sort of blocked and the other task should not have access to it. Okay, so this is a common issue. So this is also what we call a critical section. Okay, so in a critical section of the code, okay, we have to ensure that you have exclusive access to the shared resource while you're executing this critical section of the code. Okay, so you cannot have a situation where you are halfway through and then you get preempted. Okay, so if you get preempted, okay, then you must make sure that any other task is not able to access this same resource. Okay, so when task 1 is here and task 1 is writing, we cannot prevent, I mean, we may not be able to prevent task 2 from running, correct? So there may still be a context switch that happen. Okay, because maybe task 2 is considered higher priority and this is considered lower priority. Okay, so it could be a situation where task 1 was writing halfway and task 2, because it's higher priority, preempted task 1. But just because it preempted task 1, it should still not be able to access this entire buffer until task 1 finishes. Okay, so we are not saying that we do not want a preemption. The preemption might still occur. Okay, but the preempted task should not interfere or should not access this shared resource until the current task has released it. Okay, so these kind of operations are also what we call atomic operations. So when I say this is atomic operation, means I want to make sure that when I start it, I'm allowed to finish it before anybody else has access to the same data. Okay, so when we say critical sections and we made atomic, that is what we're trying to say. We're trying to say that we want to be able to have exclusive access to this data to complete what I need to do before somebody else takes over. Okay, so of course there's two issues, again, two possible sources of interference. One is the task. The other thing that we know is the interrupts. Okay, because in the system we can also have an interrupt that may want to access this shared resource. Okay, so one is task, one is interrupt. So of course for interrupts, okay, one of the things we can actually disable interrupts. Okay, so in the software we can say that, okay, during this period of time I do not want interrupts to come in. Okay, so that is one thing. Okay, but that is not OS based. That is a bit of configuring some hardware or some processor configuration. Okay, what we are more interested in is within the task or OS level, how can we ensure exclusive access to any particular shared resource? Okay, so in a shared resource, okay, like a common data structure, what can we do? Okay, so in terms of the protection, again, one is of course thread and ISR, the other is 2 ISR. Okay, but what we are more keen to understand is this, the third option, which is the between 2 threads. Okay, because within the 2 threads, anytime context switch can occur. So when context switch can occur anytime, how do I protect this access? Okay, so that is what we are more keen to explore. So this is just another example to show you. Okay, so you may have a printer, correct? A shared printer, okay, in your office or at home. Okay, and you can imagine that one computer sends a print job, another computer sends another print job. Okay, what would happen if the printer jumbled up everything? Correct? Then you get some gibberish here. Okay, so what you want is we want to make sure that the printer is able to treat each request exclusively. Okay, so even though multiple data packets may arrive through the network, okay, for both computers, okay, in this case are both threads, okay, we still want to make sure that information from one task, once it starts to be processed, I do not let it get mixed with another set of information. Okay, so that is the way to make sure that the data is handled correctly. Okay, so this is another example, okay, of how something like this can affect in an actual code. All right, so just now we talked about a buffer example or a printer example. Now let's look at it from a simple code example here. Okay, so here I have a very simple function, and this function is to increment a variable k. So k is a global variable, and I want to increment a variable k. And I have two tasks, task 1 and task 2. And both of these tasks call the same function, increment k and increment k. Okay, so basically from what we know, okay, we have task 1 and you have task 2, and we do not know right now the sequence, who is going to run first. Okay, but we know both of them are going to call the same function. Okay, increment k. Now let's first understand the concept of increment k, which is k equals to k plus 1. Okay, since we already done the first half on MIPS, okay, and assembly language programming, we already understand that this k equals to k plus 1 may not relate to a single instruction executed by the processor. Okay, because k is a, okay, so if you recall what we said or learned before, we know that k is a variable in memory. Okay, so it has some data, so it's a memory, a global variable. So when I say k equals to k plus 1, okay, I cannot perform an addition operation with data in memory. So first I need to take it and put it into one of my registers. Okay, so for example, your S0 register. Okay, then I can do the plus 1. Okay, so I can treat of this as an immediate value. Okay, and once I do the plus 1, then the result, so this is a load word or load byte instruction, correct? Then I do the add instruction. Okay, and finally I do a store word or store byte or whatever. All right, so you can see there are 3 steps to this. I need to load from the memory to the register, do the add operation, and then I store back the result. Okay, so that is what they are showing here. So again, this is just some simple pseudo code. Okay, not specifically any processor here. Okay, but the idea you can very easily relate to it. Okay, because we just covered the MIPS. Okay, so which means that when I talk about preemption, I can get preempted at any point of time. Correct? I can get preempted here, 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 here. Okay, so any point of time while I'm executing these 3 instructions in assembly, I may get preempted. Okay, in a real-time system, okay, or in an OS-based system. Okay, so let's look at what is happening. Okay, so here, even though it's written as CPU, you can think of it as task 1 or task 2. Okay, so let's assume that the current execution. Okay, if task 1 runs first, okay, let's now have 2 tasks, task 1 and task 2, and both of them are running the same increment k. Now, assuming that I follow a very nice, perfect scenario where task 1 runs first, followed by task 2, or task 2 run first, followed by task 1. So each task has 3 steps, correct? Load from memory, do the add operation, and store back, okay, to memory. Okay, so I have 3 steps. So let's assume that in a very nice scenario, I complete all 3 steps for task 1. Okay, so if I complete all 3 steps for task 1, so initially k value is 0. So when task 1 does all 3 steps, it will become 1. Correct? Then task 2 does all 3 steps. So I load the 1, increment, then store back. So it becomes 2. Okay, so that is of course an ideal situation. Okay, where I complete all of task 1 and all of task 2, or all of task 2 and all of task 1. Now let's look at what happens if suddenly there is a context switch in between. So first, initial value is 0, so I load current value 0. Okay, and then so a 0 comes here. Correct? Now I increment it, it becomes a 1. Now before I can write back, let's assume that I get an interrupt. I get a preemption here, and then I switch to task 2, and task 2 load. So what is the task 2 value loaded? It's still 0. And then I increment, so 0, and then become 1, and then I switch back again to This one is I think 1.3 first here, 1.3 then 2.3 here. Okay, so 1.3 right back means this one will become a 1. So this one will become a 1, and then finally 2.3. When 2.3 does, that means the task 2 writes back is still a 1. Okay, so you can see that if a preemption occurs, okay, in any sequential, when I execute both these tasks from 0 to becoming 2, it becomes only 1. Okay, so again, you can have another situation here, 1.1, 2.1 or whatever. Okay, so you can just sort of get the idea that the moment I switch to this multitasking environment and I have this sort of shared data, you cannot guarantee exclusive access. Okay, you cannot guarantee exclusive access, which is again very different from our single-threaded approach. Correct? In a single-threaded approach, when I write function A, and function A is calling increment K 2 times. Okay, I know that at the end of this 2 times, it will increment 2 times. Okay, there is no doubt about it. Okay, because function A will run until completion, then I'll switch to another function and so on. Okay, so it is very predictable because the flow is always step by step, line by line. Okay, but in a multi-threaded environment, you cannot guarantee that anymore. Okay, you can very much expect that any point of time, okay, before or after, in between, I may get switched out and switched back in again. Okay, so this is a issue we need to deal with correctly. Okay, and I would say what is the most challenging part of this is that the results are incorrect only sometimes. Okay, and this is, of course, I think as software developers, all of you know that this is one of the most toughest things to deal with. You know, I mean, I always say this: the best thing that can happen is a failure, a situation where the code fails all the time. That's actually very good. Okay, because if it fails all the time, then the failure is consistent. And if the failure is consistent, you can actually debug and find out what is the issue. Okay, the greatest challenge is when the failure is very inconsistent. Okay, maybe sometimes it works, sometimes it doesn't work. That is a real headache. Okay, because you do not know what caused this. Okay, you need to do a lot more debugging. Okay, so when the results are only incorrect sometimes, then you are very concerned because you can't really pinpoint and say exactly what is the issue. Okay, because it does not make you think that it's a logical a code or logical check or something like that. So there's something else beyond just the code, and that is this, correct? And this is basically another term that people use to describe is what you call race conditions. Okay, this is also called a race condition. Why? Because it is very much dependent on some timing characteristics. Okay, so if it happens that out of 10 times you test, 9 times because of the multitasking, it just so happened that task 1 complete fully, then task 2, then you think everything is correct. But suddenly at one particular point of time, suddenly there is a context switch out of order, and then you get a wrong result. Okay, so it's called a race condition because it is very much dependent on the timing relationship between the tasks. Okay, so of course, one of the option is if it's interrupt related, then we suspect that the interrupt is the one that is causing it, then we may want to disable interrupts. Okay, the disable interrupts. Okay, so that is one option. Okay, now another option, okay, that we can think about to protect, okay, to protect the shared resources is what we call using this thing called a mutex. Okay, so what is a mutex? Okay, what is a mutex? So a mutex, okay, is basically a mechanism that allows us to protect shared resources, okay, in a very proper way, okay, and is used specifically in OS-based context. Okay, so we will talk about this in a while. Okay, so I think it's a good time to go for a break. So now it's 7:35. Okay, so I think we can take about 15 minutes break. Okay, about 7:50 or so, come back here, and then we will talk about the mutex and the semaphore concept. Okay, how we can make use of these mechanisms in the OS to actually protect the shared data. Okay, so we'll go for a break now. Okay, so we'll come back about 7:50, 7:55 around that, and then we will continue. Okay, so if you have questions, you can put in the chat. Okay, so we are learning multi-threading through C. Okay, it's not through assembly. Okay, so just now the example is just to give you the idea of this issue of shared resource. Okay, but the actual multi-threading is to be done in C. Okay, so we'll go for a break. We'll come back around 7:50. Okay, and then we will look at all these mutex and semaphores. Okay, thank you. Hello. Okay, so welcome back. Okay, so let me just. So there's a question here on the software installation. All right, whether we can use VS 2019. Okay, so I haven't really tried it yet. Okay, so I'm not sure if it works. Okay, so if you have 2019 installed, you can follow the steps in the lab manual to download the zip folder. Then you navigate to that directory. Okay, and try to run the code. Okay, try to compile and see whether it can work. Okay, so if it doesn't work, usually they might give you some hints what to do, what to try, but if it still doesn't work, then you may have to try and install the 2017 version. Okay, so 2017 version I have tested, confirmed that everything is fine. Okay, so you can try. Okay, I can't guarantee that it might work. Okay, so later I will demonstrate the code, okay, the sample code, so that you can check back and see whether it works for you all. Okay, so let's continue from where we left off. So we talked about this issue of shared resources or shared data getting corrupted. So what does the OS provide? Okay, what mechanism does the OS provide to protect or prevent this from happening? So that is so the basic thing that is available in all operating systems is this component called the mutex, okay, which is basically called mutually exclusive. All right, so when I say mutually exclusive means it's either one or the other. Okay, so what happens is when you want to acquire a shared resource, okay, so in our case, let's look at the example here. Okay, let me create a new slide here. Okay, so in terms of the mutex, okay, so how it works is coming back to the same thing, okay, where I have a shared resource, okay, so a buffer. Okay, what we need to do is when I have, let's say, task 1 and task 2, both want to access this shared resource. Okay, when task 1 runs and it wants to acquire this shared resource, it must do what we call a mutex lock. Okay, so again, you may come across different terminology. Some we call it mutex lock, some may call it mutex acquire. Okay, but it's the same thing. So think of it as getting the putting a lock on it and taking the key. So if let's say somebody locks the door and takes the key, rightfully you should not be able to enter. All right. So when I do a mutex lock or mutex acquire, then I have exclusive access until a point of time when I finish using the resource. Again, in my case, I go through everything in the buffer, finish already, then I say mutex release. Okay, mutex either unlock or somehow we call it mutex release. Okay, so when I call mutex unlock or mutex release, then somebody else can take it. Okay, so how does this mechanism work? Okay, how does this mechanism work? It comes back to the idea of the state transition of the task. Okay, so if my task one is currently in the run state, okay, and I say mutex lock for this buffer, then I am telling the OS that this buffer is now exclusive to task one. All right, it's exclusive to task one. Now, multitasking in a multitasking environment, the context switch can happen anytime. Right? So let's imagine that right now I have acquired the lock already, and I'm halfway through my task. All right, that means I'm halfway through my processing of the data, and then at this point of time, suddenly there is a context switch. Okay, a context switch, and this context switch allows task 2 to run. Okay, so until this point of time, task 2 was maybe in a block state. Okay, maybe it was blocked waiting for something else. Okay, and at this point of time, suddenly something else happened, some event, some interrupts got triggered, and it got unblocked, so it went to the ready state. Okay, and let's assume that task 2 is a higher priority task. This is a low priority task. Okay, so task 2 being a higher priority task, the moment the task 2 becomes ready, okay, it goes to the top of the queue, and the scheduler sees that the task 2, which is a higher priority task, is in the queue. So since we are dealing with a preemptive OS, it will automatically switch task 1 out. So task 1 will at this point of time go to a ready state, and task 2 will go to a run state. Okay, so when task 2 goes to a run state, okay, what happens? Okay, the first thing that the task 2 tries to do is what? Because the task 2's objective is actually to also deal with this buffer. Okay, it's also to deal with this buffer, and since the rule is that the buffer is protected by this mutex, I need to first lock the mutex. That means I need to ensure exclusive access to this resource. So the first thing that the task 2 will want to do is you will want to do a lock. Okay, you want to do a lock. But what happens? Since task 1 already did the lock. Okay, since task 1 already did the lock, okay, it is no longer available. That means the OS knows that some other task has already locked this particular resource and it's not available. So when task 2 tries to do the lock, the OS will say that it cannot do the lock, okay, because it has already been locked by somebody else. Okay, and since it cannot proceed without the mutex, that means it cannot access the resource, it will go back to a block state. Okay, it will go back to a block state. So this ensures, okay, this mechanism actually ensures that even though I get preempted, okay, even though task 1 got preempted, okay, it doesn't matter because access to this shared resource is still bound to task 1 until a point of time when task 1 releases the mutex. So even though task 2 got a chance to run, task 2 is higher priority, it is fine. Okay, because task 2 still has to wait until the mutex is released. So task 2 will wait or will be in a block state until a point of time when the task 1 finishes and releases the mutex. When task 1 finishes and releases the mutex, okay, then the OS will come in and see that, okay, task 2 was actually blocked waiting for the mutex, so it will now give that mutex. So it's just like the key was originally with task 1, and now that task 1 is done, the key is now passed to task 2 because task 2 was waiting for the key, it was blocked waiting for the key. All right, so eventually task 2 will get the mutex, and so it will go to the ready state, and from the ready state it can go to the run state, and this time when it goes to the run state, it already has the mutex, so you can go in to access the buffer. Okay, so that is actually the whole mechanism behind how the OS actually manages shared resources very nicely for us. Okay, so we don't need to worry about anything. Okay, as long as we use the mutex correctly, okay, we will ensure that whoever is the first one to lock the mutex will get exclusive access until the lock is released. Okay, so even if a context switch happens, you still do not need to worry because the mutex is still having the lock for the shared resource. Okay, so that is basically what is happening over here. Okay, so this is all the explanation. All right, but eventually, okay, only one thread can own the mutex at any point of time. So once a thread owns a mutex, any other task or thread that wants to own it will get blocked until the mutex is released. Okay, so that is basically the idea behind the mutex. Okay, so right now, basically all I need to do is I just need to make sure that the way to protect my resource is very simple. I need to make sure that I put in the mutex span and mutex post. So this is the terminology used in the OS that we are going to be using. Okay, but you will, the idea is the same, whether it's span and post, acquire and release, whatever, it is all the same. Okay, that means we first lock it. Okay, so the whole idea is I first lock it, and after that I unlock it. And how long do I lock and unlock? Only for the duration of the shared resource. Okay, so you don't lock and unlock for the whole thread, huh? No. But we only do it when we are dealing with a shared resource. Okay, so if I happen to require access to the shared resource, then that part of the code alone, before and after I lock and unlock. So that will ensure that whichever task runs first and acquires the lock will get to use the shared resource completely until it releases the lock. Okay, so that is mutex. Now another thing that is very similar to mutex, okay, very similar to mutex is this thing called semaphore. Okay, so it's very similar, okay, except that in semaphores can be used to manage events, okay, as long and also manage access to shared resource. Okay, but generally, okay, as a rule of thumb, we say that for shared resources we use mutex, for resources we use semaphore. Okay, but we can also use semaphore for resources, okay, which I will also explain in a while. Okay, but let's first understand the concept of semaphore. So the whole idea of semaphore is in the idea of managing events. Okay, we can think of semaphores as a mechanism to actually provide some signal from one task to another task. Okay, and you can think of it in another way where you can say that one is a producer, the other is a consumer. Okay, so what do we mean by this? Okay, so basically a semaphore contains a count. Okay, and this count is basically tracking the number of resources. Okay, the number of resources available. Okay, so what do you mean by number of resources available? Okay, so you can think of it as maybe the amount of memory blocks that you have. Okay, a simple way. Okay, so imagine that you have 3 different buffers available. Okay, buffer 1, buffer 2, buffer 3. Okay, which any task can use, okay, when they need to do some storage of data and do some processing. Okay, so maybe this is all the memory that is spare and is available. Okay, so 3 buffers. Okay, so you can use semaphore, okay, as a mechanism to manage access to these 3 buffers. Okay, and what happens is whenever a task requires a buffer, it will take a semaphore. Okay, so when it takes a semaphore, what happens? Okay, the count will be decremented. Okay, the count will be decremented. So initially I will say my count is 3. Okay, whenever I take, I will decrement. I take, I'll decrement. I'll take, I'll decrement until it becomes a 0. So once I hit 0, what happened? Okay, you cannot get any more resource, correct? Until a point of time when somebody posts a semaphore. So when you say somebody posts a semaphore, what happened? So let's assume that currently I have 3 buffers. So task 1 comes in and it takes, so it becomes 2. Okay, task 2 comes in and takes, becomes 1. But after that, task 1 say, okay, I'm done already. I'm done in the buffer. I want to give back. So it becomes 2 again. Okay, so whenever a task gives back a semaphore, that means it is done with the resource, the count goes up. When another task comes along and says, I want a resource, the count goes down. Okay, so of course, once I hit the maximum count, I will not be able to increment further. And similarly, when I hit 0, I cannot decrement further. Okay, so the whole idea of semaphore is you are managing a group of resources. Okay, and as and when tasks require resources, they can acquire a semaphore, and when they're done, they release the semaphore. Okay, and that is done, okay, using what we call these 2 functions, OSSemPen and OSSemPost. Okay, so whenever I want to take, so this is equivalent to semTake, and this is equivalent to semGive. Okay, so when I say semPen or semTake, I'm acquiring a resource. Okay, so the count will go down. When I give, I increment. Okay, now what happens, okay, if I try to take, okay, and it is not available? Okay, so a task comes along and it says, I want a buffer, but the count is already 0. So I cannot give you the buffer, correct? So what will it do? It will make the task go into a block state. Okay, it will make the task go into a block state. So this is again one of the mechanisms to ensure that if a task requires this resource, if the resource is available, it will get it and it can carry on. If the resource is not available, it will go to a block state. Okay, now when a task go to a block state, how can it get unblocked? It can get unblocked when the resource becomes available, correct? So whenever somebody say semPost or semGive, that means I'm giving back the resource. I already finished, I'm giving it back. So when I give it back, what happens is the OS will look at the block processes, okay, in the queue, and allow one of those tasks that are currently blocked to be unblocked. That means it can join the ready queue. Okay, so this is what we mean by a task is blocked because it's waiting for a resource. But in this case, the resource is actually managed by a semaphore. Okay, so the moment a semaphore becomes available, then the task that is blocked will become unblocked and you can join the ready queue. Okay, so let's look at this example over here. So in this example, we are starting out with 3 resources. Okay, so the term here is P is equivalent to take, and I think B is equal to give. So when I say PS, that means I'm saying I want to take a resource. Okay, so I take a resource. So from 3 becomes 2. Then another task comes along and says I want to take another resource. Then becomes 1. And the first task that took the resource wants to give it back. Okay, so since it gives it back, the count goes up by 1. So from 1 it becomes 2. Okay, then another task comes along, take the resource, 2 becomes 1. Then another task comes along, take a resource, from 1 becomes 0. Okay, and once it is 0, another task comes along, okay, and says I want, but then there are no more resources. So if there are no more resources, it will join the queue. Okay, so X and Y will be put in the queue. Okay, so once they join the queue, they are waiting. Okay, so initially you have X. Okay, so this is the queue. Okay, you have the queue, so you have your X, and then you have Y. Okay, so X and Y in the queue. Okay, now when X and Y in the queue, they are both waiting. All right. Now X join the queue first, followed by Y. So when another task comes along, okay, that releases the resource. So one of the tasks here, the purple color task that acquired the resource, is now returning it. But when he returns it, what does the OS see? The OS sees that I already have people waiting in the queue. So if there are people waiting in the queue, when I return, the count doesn't go up. Okay, the count doesn't go up because I take from one person and immediately give it to another person. Okay, so I take from the task that is returning it, and I immediately give it to the person that is in the queue. Okay, which is X. So X will go out of the queue and go to the ready state. Similarly, when another person comes along, okay, and does the same thing, they return, okay, the count doesn't go up in this sense. It still stays at 0 because there's already somebody else in the queue, which is the process Y. So I will also remove the Y from the queue. Okay, and then I go on. Okay, when there's nobody else in the queue and then I release, then the count goes up. Okay, so X and Y. So X gets the first semaphore and Y gets the second semaphore. Okay, so that is basically how we can manage, okay, resources more effectively using semaphores. Okay, so in this case, okay, the initial semaphore count, okay, okay, this example what we have is we are saying that the initial semaphore count is 0. Okay, so if originally my semaphore count is 0 and I try to do a pen or a tick, okay, what will happen is, since there are no more resources available, it will cause my current thread to go to a block state. Okay, and I will remain in this block state until somebody releases the semaphore, okay, by calling a post. So once the semaphore is released, then it will come or be allocated to the task that was waiting for it, and that task will become unblocked. Okay, so the count is still 0. In this case, the count is still 0 because it is basically taking from the person who posted it and giving it to the person who was waiting for it. Okay, so the count is still 0. Okay, so this is basically how we can relate mutex and semaphore together. Okay, the way in which we can use semaphore in a similar manner as mutex is by declaring it as a binary semaphore. So a binary semaphore basically means 1 or 0. So if I declare my semaphore to have a count of only 1, then only one task can take. Correct? And the moment one task take, the other task must wait. So it is the same concept as mutex. Okay, so if I have the same buffer over here, okay, task 1 and task 2, okay, when task 1 run, it says sem take. Okay, so the semaphore initial count is 1. So the moment it says sem take, what happened? The count becomes 0. Okay, and then it can do whatever it wants to do. But if it gets preempted, okay, and then task 2 runs, when it does the sem take, it comes to the same issue, right? Because the semaphore is 0, you will go to a block state. Okay, so the behavior can be very similar, correct? When I use mutex and when I use semaphore with a count of 1, so we call it a binary semaphore. Okay, so this is just one example of how you can sort of use semaphore in a similar fashion to mutex. Okay, so that is basically how the mutex and semaphores work. Okay, so now what I want to do is I want to instead of going through the rest of the OS concepts, okay, we are going to stop this here first, and we are going to go to the software side. Okay, so let me open up the software, and we're going to understand some of the things and the way in which the code is written. Okay, so that you have an idea of what is happening, and when you run the sample code that I given you. Okay, so this sort of we're going to jump in front a bit all the way to the MicroC OS 3 part. Okay, so in this slide from 57 onwards, okay, these few are basically all the various task related functions. Okay, so but instead of going through them over here, I'm going to go through them directly from the code. Okay, so this is basically the code that you are supposed to open up. Okay, based on the zip file that are provided, and after you install the VS 2017. Okay, so the OS that we are going to be using is this OS called the Preemptive OS. Okay, so there are a lot of OS in the market. Okay, even though we are familiar with those like Linux and Windows and all this other stuff, okay, there's a whole host of other operating systems that can work on many computing platforms. All right, so ThreadX, QNX, VxWorks, Preemptive, and so on. So there's a lot of them. Okay, so if you're ever going to work on OS-based products, okay, on maybe any particular standalone controller board, okay, I think most of you may have played around with, let's say, Arduino, Uno, or some other boards that you're familiar with. Okay, so if you want to run an operating system on that, then you need to look around for OS that is targeted towards such devices. Okay, generally, running let's say Windows or Linux or anything works fine on all sort of general purpose computers. Okay, so in this example, or in this OS Preemptive, okay, we are going to be looking at how OS based code is written. Okay, and how we can leverage the OS, okay, to develop a multi-threaded code. Okay, so let's look at the first part of this. Okay, so even though we are having a multi-threaded code, okay, the starting point, okay, is always main. It's always main. Okay, because no matter what, you always have to start off in a single-threaded environment first before you can boot up the OS. Okay, same like your Windows as well. All right, when you start up your PC, the first thing that runs is your single-threaded code, your BIOS, and all this low-level hardware configuration. Then only you see the Windows logo come up and says Windows is loading. Okay, so you can never immediately load the OS. You need to do some very low-level setup first before the OS can actually be loaded. All right, and that initial code is always still single-threaded. Okay, is that the standard line by line, either in assembly or C. Okay, so the starting point is always the main. All right, so if you look at the main over here, okay, there are things here that are done, okay, which relate to all the low-level libraries to configure the hardware, the resources that the OS needs, and so on. Okay, so for example, initializing the CPU, initializing the memory, and all this other stuff. Okay, so I will not go through all of this. Okay, what we want to focus on is those OS specific functions. Okay, so the first OS specific function is this thing called OS init. Okay, so what is OS init? OS init is basically a library that is called to set up all the low-level libraries and APIs that you need to run the OS. Okay, so it is like making sure that whatever the OS needs is properly initialized and set up in your environment. Okay, so that is the initialization of the OS. Okay, so that is the first thing that the code will do. Okay, next is this app OS set all hooks again is something you don't need to worry about. It's again related to making sure that the OS is able to link up with all the APIs and drivers of the system. Okay, what we are interested in is the next few things. Okay, so in this example, we are first going to create this thing called OS task create. Okay, so what is OS task create? So this is where we can create a task, okay, that we want to run in the system. Okay, so when we create a task, okay, you can see that it has a lot of parameters here. Okay, there's a lot of parameters. Okay, what are all these parameters? So let's come back to our slides here. Okay, so under OS task create. Okay, so you can see that there are a lot of these parameters here. Okay, so what are the important things here that we need to specify? Okay, so the three important things are this first three over here. Okay, followed by the stack. Okay, and the priority. Okay, so these are the few important things. Okay, when you're going to create your own task, okay, for the assignment, okay, you can just copy paste an existing template, okay, and then modify from there. Okay, so let's look at the example again over here. So in this task create, okay, the actual task name is this startup task. Okay, so there must be a function sort of to say that has the same name. Okay, in this case startup task. So this is the task. Okay, so even though I use the term function, okay, it is actually what we call a task. You're creating a task that we manage by the OS. Okay, this name of the task, okay, is actually startup task. Okay, so this name here must match whatever you put here. Okay, now this name, okay, is more of a name for the debugging. Okay, so when it is managing the or running the program, okay, it will use this particular name or this string here to relate to this task. Okay, so this one can be anything. You can input anything you like. Okay, that doesn't really matter. Okay, what is really important is this. Okay, and besides this, the very first parameter is the TCB, the task control block. Okay, so this task control block is basically the block that contains all the information regarding the stack, the registers, the program counter, and all the other sort of context of the task that it needs, so that it makes sure that when I switch out and I switch back, I'm always able to continue from where I left off. Okay, so this task control block, okay, where is it defined? Okay, so this task control block you can see is defined here. Okay, so using this definition OSTCB, you put a name. So in this case, startup. So usually the easiest way is you just follow the same name that you're using for the task, and then you add TCB behind task control block. Okay, so that is the one over here. Okay, then the other parameter here is this, the priority. Okay, so this is the where you can configure the priority of the task that you're creating. Okay, so where is this defined? So in your project, okay, if you look here on the solution explorer on the right, okay, for each solution, okay, there is a file here called appconfig.h. Okay, under appconfig.h, you will see that the definitions and the priority values are written here. Okay, so the priority numbers are in reverse. That means the smaller the number, the higher the priority. Okay, so I would suggest do not put any priorities as 0, 1, or 2. Okay, start from 3 onwards. Okay, generally you can put them as even similar priorities. Okay, it will still be fine. Okay, again, it all comes back to how you come up with the overall architecture of the software. Okay, so even if I declare all a similar priority, you can still get everything to work nicely. Okay, as long as the idea behind it is, the architecture behind it is correct. Okay, but okay, in this example, we have 3 tasks, okay, 3, 4, and 5. Okay, so let's come back here. So this is where you define the priority. Okay, now these next three things are the important ones. Again, important because you need to make sure they're correct. So these are the address for the task stack. Okay, the actual memory size that you are setting aside. Okay, and the size that is specified. Okay, so what I would suggest is when you are creating your own task, you just copy this whole thing, and whatever is related to the task name you change. Okay, so if you're creating a task A, then all of these startup tasks will all change to task A. Okay, so these are the things that you need to configure and set up correctly, these parameters. The rest of it you can keep it as it is. Okay, now let's understand what is happening step by step. Okay, give me a minute. Let me open up my OneNote. Okay, so where are we now? Okay, so let's try to make sure we understand this very clearly. Okay, so that you understand the whole flow of what is happening. Okay, so what has happened so far? Okay, so we have our main program. Okay, and the main program has done some initial OS initialization. Okay, so there are a few other functions there. Okay, so you don't need to worry about everything. After that, what I have done is I have called OS. Let me use the correct term. Task create. Okay, and this task that I created is basically what we call the startup task. Okay, so I've created this task called the startup task. Okay, and so far I'm still in the single threaded environment. Okay, so everything is going line by line. Okay, so I create this task. Okay, after that, okay, this semaphore. Okay, this OSM create. Okay, so let's look at this OSM create. So this OSM create is to create a semaphore in the OS. So there are a few parameters here. Let's come back to our slides here to look at what are all these parameters for. Okay, so OSM create is to create and initialize a semaphore. Okay, and there are a few parameters here: the OSM name, the character name, and the count. Okay, so as before, the actual semaphore name and the count are the two important things here. All right, so this text name is, again, you can put anything you like. Okay, but this MySem is the actual semaphore name that you're going to be using, and this is the count. Okay, so the initial count of this semaphore is 1. Okay, so this MySem, where is this MySem defined? That is defined over here. So you must use the type OSM and put a name here, MySem. So I'm declaring that I'm having a new semaphore. Okay, and the name is MySem. Okay, so I created a new semaphore and the name is MySem, and I put initial value of 1. Okay, so that is the next thing that I've done over here. Okay, so I've created a semaphore called MySem and I put it to a value of 1. Okay, so all of that is happening, and then I call OS start. Okay, so this is basically the critical point. Once I call OS start, okay, once I call OS start, I am actually starting the multitasking. That means I am moving away from the main, the single threaded environment, and now moving towards a multitasking environment. Okay, so until this point, I was still executing sequentially, okay, line by line. But once I call OS start, okay, I immediately switched over to the multitasking environment. Okay, and once I switch over, okay, I should not come back, okay, unless something really bad happens and the OS crashes or something. Okay, but as a general practice, usually what they will do is they will put another while loop here. Okay, after the OS start. That means if for some strange reason the OS crashes and something goes wrong and you come back to the main, you are still inside this while loop here. Okay, but you should actually never get here. Okay, because once you start multitasking, your objective is you are now in a multitasking environment. Okay, so once I start call OS start, I'm switching over. Okay, so basically that is the key point. So right now here, I'm calling OS start. Okay, and once I call OS start, okay, so this is basically a loop which you never get to. But once I call OS start, basically you are no longer in this single threaded environment. You are switching to a multi-threaded environment. And once I switch to a multi-threaded environment, who is the main person? Okay, who is the main person that decides everything? Okay, that is your scheduler. So I'm no longer in this single threaded environment. I'm now in a multi-threaded environment where the scheduler and the OS kernel come in to manage everything for me. Okay, so now the scheduler kicks in. Okay, because the OS environment has started, what will the scheduler do? Okay, the scheduler's job is always very simple. It will look at who is in the ready queue. Okay, and since we know that over here, I've already created a task called startup task. So that startup task is actually in the ready queue. Okay, so inside my ready queue, okay, I have a startup task. Okay, so again, like I said, the while loop is just there as a sort of a mechanism to catch any potential issue where the OS fails. All right, but by right, this you will never get to the loop. Okay, because as long as the OS is running, you will already be in a multi-threaded environment. Okay, so even if you remove this loop, you should not see anything happen. Okay, because you never expect to come here. Okay, so once the OS has started, okay, and the scheduler kicks in, okay, you are already in this multi-threaded environment. Okay, and in the multi-threaded environment, the scheduler comes in and it looks at who is in the queue. So it sees that startup task is in the queue. Okay, so when startup task is in the queue, okay, and there's nobody else in the queue, so it will automatically transition startup task to go from ready to run state. Okay, so what will happen is we'll look at startup task. Okay, so initially it's in the ready state, and then it will go to the run state. Okay, so once it goes to the run state, it will start executing. Okay, so what does startup task here do? Okay, so let's look at startup task. Okay, so we will again ignore some of this other stuff here. Okay, so again, all this stuff here is related to setting up some parameters to help us with the debugging and tracing of the OS and what's happening. Okay, so we can safely ignore all of this now and focus on the actual action here. All right, and that is startup task is calling OS task create. Okay, 2 times. Okay, it's calling OS task create 2 times. One for task A and the other for task B. Okay, so you can see the template is the same. Template is the same. Only thing is you change whatever is related to the new task name. So this is task A. So all of this is related with task A. If it is task B, all of this is related with task B. Okay, so it's the same template. You just copy and paste, and then you make the changes depending on the task name. Okay, so basically what is happening here is your startup task is now going to create 2 other tasks, which is okay OS task create task A. Okay, and after that it's going to create again the same thing, but task B. Okay, so first task A and then followed by task B. Okay, so you're going to create these two tasks, and after you create these two tasks, task A and task B, it goes into this loop. Okay, this while one loop, which continuously cause this OS time delay, HMSM. Okay, so eventually what is this? OS time delay, HMSM. Okay, so come back here. Okay, so this is basically to delay itself. Okay, that means it put itself into a block state for a period of time. So this HMSM is hours, minutes, seconds, and milliseconds. All right, so in our code, what we are doing is we are calling ourselves to delay 1 second, but it's just an infinite loop. Okay, so you can just think of it that this whole thing is just nothing more than infinite delay loop. Okay, infinite delay loop that blocks itself forever. Okay, so you can sort of take it that I will be permanently blocked. Okay, so you can think of it as block. Go to a block state. Okay, so there's nothing else that I'm going to do already. Okay, because once I create the two tasks over here, task A and task B, my code inside here, which is basically to block myself indefinitely. Okay, so let's see what has happened. Huh? So when I created task A and task B, what happened? That means since startup task already came out of the ready queue, okay, task A first joined the queue now, followed by task B. Okay, task A was created, followed by task B. Okay, of course, we also need to look at the priority, correct, on who was on the priority level. So we can check back over here, task A and task B priority under app config. Okay, so task A priority is given a smaller number, task B is given a bigger number. So task A will be in the top of the queue, followed by task B. Okay, task A followed by task B. Now, so we know that inside our ready queue, this is what is happening. Okay, task A and task B. Okay, but both of them are still in the ready queue until the current task goes to a block state. Okay, until the current task goes to a block state. So the moment the current task goes to a block state, it is not in the queue. Okay, it's not in the queue. So the scheduler comes in, correct? Because the moment the current task goes to a block state, there's nobody in the run. That means nobody is in the CPU. So the scheduler comes in and looks at the ready queue. And it says that, okay, now task A is in the front of the queue. So we will allow task A to transition from the ready to the run. Okay, so let's look at task A. So task A is here. Is going to be from the ready queue, it will transition to the run state. Okay, so now that task A is running, okay, let's look at what task A is supposed to do. Okay, so what is task A supposed to do? It's supposed to do a print. We're supposed to do a printf of task A, but before and after the print, it does a OS sampan and OS post. Okay, so why do we do a sampan and post? Basically, we want to treat the print, that means the screen. Okay, so in this case, the printf means we are trying to print to the computer screen. Okay, so we want to treat the computer screen as a resource. Okay, so we want to make sure that when task A is printing the screen, it should not printing something to the screen, it should not get preempted by any other task. Okay, so when task A, before it is printing to the screen, it acquires the resource. In our case, the resource is the computer monitor or the screen. Then I print out what I want to print out, and after I finish, I release the semaphore. So I take the semaphore and I release the semaphore. Okay, now let's look at OSM pen and OSM post. Okay, come back here, semaphore usage. Okay, so for SEMPEN and SEMPOST, okay, what happens? So in SEMPEN, basically what you do is you take the semaphore, okay, and then you decrement the count. Correct. And if it is 0, when you try to take it, then you go to a block state. Similarly, okay, if it's post, I release a semaphore, that means I increase the count, okay, and then if another task is blocked, then that task may get it. Okay, so in terms of SEMPEN and SEMPOST, the concept is similar to what we discussed. Okay, so we only need to worry about the first two parameters now, or the first parameter. In this case, we are taking this semaphore, mySem, okay, and this 0 over here. This 0 over here, SEMPEN, what is that 0 for? Okay, that 0 is basically what we call a timeout. Okay, so for now, we will treat the timeout as 0. Okay, and what does that mean? That means I will not wait for the semaphore. I will want to take the semaphore. Okay, but if I don't get the semaphore, I will go to a block state. Okay, I go to a block state. Okay, so that is why we say blocking over here. Okay, but once I get the semaphore, I can print out, and once I finish, I can release the semaphore. Okay, so let's look at this again. So I take the semaphore, correct? So because the semaphore is tied to the resource, which is the screen, and once I get the resource, means I can print to the screen. So I do a printf. Once I finish, I do a post. All right, and once I finish with the post, that means I return the resource. That means somebody else can use the screen. I call a delay, okay, for 1 second. Okay, I call a delay for 1 second. All right, so when I call a delay for 1 second, what happens? Somebody else can run. So who else is in the queue? Okay, so we know that task B is in the queue. Okay, so task B can only run when task A goes to a block state. All right, so let's see what is happening. So task A is going to run, is first going to take the semaphore. Okay, so until this point of time, task B is there also. Okay, task B is there, but it's in a ready state. It's in a ready state. Okay, until a point of time when task A goes to a block state. Okay, so task A is going to run, is going to take the semaphore, is going to print out task A. Okay, and then it will give. Okay, that means return a semaphore. Okay, and after it gives back the semaphore, then it calls the OS delay. So OS delay for how long? For 1 second. OS delay for 1 second. So after this, it was going to go to a block state for 1 second. So at this point of time is where, since the task A has gone to a block state, it is not using the CPU, then the OS comes in and see who else is in the queue. So task B is in the ready queue. So since task B is in the ready queue, it will allow task B to transition out of the ready queue at this point of time to go to the run state. Okay, and when task B goes to the run state, what will it do? It will do the exact same thing. Okay, so if you look at task B's code over here, Okay, task B's code is the exact same thing. You will take the semaphore, you will print out task B, okay, and then you will post the semaphore, and then you will do a delay again. Okay. Okay, so your questions all I will answer in a while. Let me finish this and address your questions. Okay, so task A, task B. So when task B runs, it's going to do the same thing. Okay, it's going to say Sam pen. Okay, then you're going to print task B. Okay, and then you will Sam post. Okay, and then you're going to do the same thing. OS delay. Okay, and so you can see that there could be a point of time where both the tasks are in a block state. So this is also block. Okay, this is also block. Okay, but since task A was the first one to call the OS delay, okay, at some point of time, task A will come out of the block state. Okay, come out of the block state, and then will go to a ready state. When it goes to the ready state, it will join the ready queue, and then once it joins the ready queue, it will again be transitioned to the run state. Okay, so that is why we say that if you look at this, both task A and task B, everything is written inside a while one loop. So the thing or activity that I want to carry on will keep on repeating. Okay, we'll keep on repeating indefinitely. Okay, so let's just run this first. Okay, let's just run this first, and then we observe what happens. Okay, so I'm going to build. Okay, so you can see from the printout task A, task B, task A, task B, task A, task B, and so on. Okay, so this is continuously running every second. Okay, every second you're printing this out. Okay, but even though we print out as task A, task B, okay, we can see that actually there's a lot of things happening in the background. Okay, with all this multitasking that's going on. Okay, so this switching to and fro is all happening continuously in the background. Okay, the context switching, the saving of the state, restoring of the state, all of this. Okay, so we see it as task A and task B, but a lot of things are happening in the background. Okay, now, so let me first look at your questions before we go on to the next part of this. Okay, so how to change priorities? Again, the priority level is again currently set inside this file called the app.config.h. Okay, so under app.config.h, you can set the priority number. Okay, so the smaller the number, okay, so you should not use any numbers 0, 1, and 2. Okay, but 3 onwards you can use. Okay, so the numbers that are smaller have higher priority. Okay, bigger numbers have lower priority. Okay, so that is where you can set the numbers. Okay, so the next question is delay sort of a practical solution? Okay, so definitely delay is not a practical solution. Okay, because again, delay is giving a time, correct? And in a real world situation, we can't really say how much, how long. I mean, it's not usually time related, in a sense that mostly it is event related, correct? Some event happened, you want to respond. Okay, so this concept of using time is just a demonstration only, sort of showcase how this environment works. Okay, but in the next few concepts that we'll be covering, you won't use delay. Okay, you will use a more proper sort of technique of how to synchronize the behavior of tasks. Okay, so this delay again is just to demonstrate only how this sort of environment works. Okay, in subsequent demonstrations, we will look at how or a more proper way. Okay, so because if I really want to print task A, task B, task A, task B in sequence, okay, using 2 different tasks, then a proper technique would be to make sure that after I print task A, I sort of send a signal over to task B, and task B should sort of get unblocked, do the printout, and send a signal back to task A. Okay, so I should have a proper mechanism to allow these two tasks to synchronize. Okay, but again, those are concepts which we will cover in future lesson. But for now, we just use this delay concept. Okay, so why the U? Okay, so the U is again just a coding convention. It stands for unsigned. Okay, but you don't need to put the U. Without the U, just a number is also fine. Okay, without the U, the number is also fine. Okay, so this is basically what we have. Correct? What we have in terms of task A and task B. Okay, and from the understanding and what we have seen so far, we can see that the semaphore is tied to this resource. So we take the resource, we print out what we want to print out, and we release the resource so somebody else can take over. Okay, now let's do some things a bit differently just to see whether our understanding is correct. Okay, now what I'm going to do is I want to make a slight change now, okay, to the code. So instead of just task A and task B doing the exact same thing, task A is going to do this. Okay, going to take the semaphore, print and release. Now task B is going to take the semaphore, okay, but it is not going to release the semaphore. Okay, task A is going to take the semaphore and release it as how it's supposed to be done, but task B is not going to do it. Okay, task B is not going to do it. It's going to do only part of it. It's going to take a semaphore, but it's not going to release the semaphore. Okay, so now let's have an idea and see what do you think will happen. Okay, so let me get your views first. So what do you think will be printed out? Okay, so in the code, task A will print, task A will follow. That means it will take semaphore, print out, and it will release. Task B will take the semaphore, but it will not release the semaphore. Okay, so if you've not used this poll everywhere before, you just need to open up any browser to go to this link, pollev.com/rsnus, and then you can submit your answers there. Okay, so yeah, most of you have chosen task A, task B, nothing after that. Okay, some of you think it's task A once only. Okay, so let's and this. Okay, so let's come back to this. All right, let me compile the code and then let's run it. Okay, so when I run it, let's see what happens. So you see task A and task B and nothing after that. Okay, nothing after that. So I think most of you got it correct. Okay, so why is this so? Okay, why is this so? Because what has happened is task A runs, it acquires a semaphore, it prints, and then it releases the semaphore. When task B runs, it takes the semaphore, it prints. Okay, and then it doesn't release the semaphore. Okay, so if I look back at this timeline, what happened is we came until here. Okay, so everything was good, correct, but I did not return the semaphore. So I did not return the semaphore. So let's assume that I never returned, correct, and then I call the OS delay. Okay, and now both of them are going to a block state, and eventually task A comes out first. So when task A comes out and it goes to the run state, okay, let's say it already go to the run state here, the first thing it tries to do is it tries to take the semaphore. Okay, but what is the semaphore count? The semaphore count is 0, because when this task B took the semaphore, it became 0. Correct? Is already taken. So when the task A tries to take the semaphore, the count is 0. Okay, so at this point of time, the semaphore is already 0. So it can't take the semaphore. It goes to a block state. Okay. Similarly, okay, when task 2, okay, eventually comes out of the block state. Okay, eventually comes out of the block state and it tries to run. The first thing it tries to do is it also tries to take the semaphore, sempen. Okay, and then it faces the same issue. Okay, faces the same issue because the semaphore count is 0. Okay, sometimes, okay, some students may think that, hey, but task B is the one who took the semaphore, right? So if we took the semaphore, it should still have the semaphore. Then it should still be allowed to carry on anyway. Okay, so that is again traditionally we may think like that in terms of variable or something else that we acquire, but in terms of the OS, it follows the rules very strictly. Okay, that means as far as is concerned, if you say you want to take a semaphore, it follows the rules to say that if the count is anything greater than 0, you will get a semaphore and you will decrement the count. If the count is already 0, it will go to a block state. Okay, so in this case, since the semaphore count is 0 and it tries to acquire, it cannot get, so it goes to a block state. Okay, it goes to a block state. So that is what is happening here. So even though it acquired a semaphore, but now it tries to call sempen again. And since the count is already 0, it will also go to a block state. Okay, so that is why it will permanently, both tasks will be in a block state because both of them are now waiting for somebody to release a semaphore. Okay, but actually nobody is releasing a semaphore, so nothing else happens. Okay, now let's do one more example here. Okay, and what I'm going to do is this same code, but now I'm going to even block off this. Okay, okay, so coming back to our understanding, our understanding is the semaphore is tied to the resource. You take the semaphore, you can use the resource. What is the resource? The ability to do a preemptive. So task A is taking the semaphore, print, and it is a semaphore. Task B is not taking or not releasing, but that it tries to do a print. Okay, so what do you think will happen? Okay, so let me try this one more time. Give me a minute. Okay, so again, most of you believe it's task A, task B, and nothing after that. And some say task A once only. Okay, so let's look at what happens. Okay, let's look at what happens. Okay, so again, the code task A is taking and releasing. Task B is not doing anything. I mean, it's not taking or releasing semaphore. It's just trying to directly print. Okay, so let me build the code. Okay, and what do we see? We see what we saw initially, task A and task B, task A and task B, as if nothing changed. Right? This was the exact same thing that we saw in the beginning. Okay, task A and task B continuously alternating. All right. So why is it this way? Okay, why is it this way? Okay, when task B is not even following the rules, correct? Okay, because the rules that we said was that the semaphore is tied to the resource. All right, and task A is following the rules. Okay, so it's getting printed out, but task B is not following the rules, but it's still getting printed out. Okay, as if nothing happened. Correct. So why is it so? So this comes back to a very, very important concept, okay, which we must understand once we go to multitasking or multithreaded programming. And that concept is the idea that a semaphore is tied to a resource is only in the programmer's mind. The OS has no idea why you created a semaphore. Okay, the OS has no idea why you created a semaphore, what it is used for. Okay, the OS just treats a semaphore or any other feature according to its rules. Okay, the idea that a semaphore is tied to something physically or to anything else, okay, is only in your mind. Okay, so when this code was written, I kept trying to tell you that the idea that the semaphore is tied to the print, okay, it is linked to the print because that is the intention of the semaphore. But the OS does not know that. Okay, so as far as the OS is concerned, it just follows the rules. So even if I were to block off all the semaphore, it makes no difference because end of the day, it will come to this task B, it will say, okay, I'll do a print, I'll do a delay. Okay, only if I take a semaphore and I don't take return back, okay, then I do not fulfill the proper usage of a semaphore, then things go wrong. But if I totally don't use the semaphore, I can still do the printf to my task B without any issue. Okay, without any issue, because the OS does not know that this MySem is tied to a printf. There is no link. The link is only in your idea, in your mind. Okay, so that is why even with or without the semaphore, I can still go ahead and print. Okay, and this comes back to a very, very important thing, coming back to the idea of the mutex just now. Okay, so in this, okay, concept of the mutex protecting a shared resource, if the task one follows the rules and locks the mutex and then says that I must acquire the buffer and then I do it, but task two does not follow the rules. That means it tries to go ahead and access the buffer without taking the mutex, it will still get access to the buffer, and then you will still have the same data corruption problem. All right, so the OS can only gives us the tools to help manage these situations. Okay, but it is still our responsibility to make sure we use these tools correctly in the way we design the code. Okay, so it's just like, you know, if I say that this door is locked and you can only open the door through the key, Okay, but if somebody else comes along and says that I will try to climb through the window, you can't stop the person. They will still find a way to break the window or something and still get inside the room. So that is exactly what is happening. Okay, so if everybody follows the rules and says that we can only enter through the door with the key, then everything is fine. Okay, but if somebody comes and says I will break the window and enter through the side, then you can't stop things from happening. Okay, so that is again a very important concept. Okay, so that is something that I wanted to demonstrate here. Okay, the semaphore being tied to the resource of the print, okay, is actually a concept that we have in our mind, but when we implement it, we need to make sure we implement it correctly. Okay, so basically that's what I wanted to cover for today, just to make sure that we go through this entire code step by step, everything, you know, from the very beginning, the main, all the way to the task, so you understand how the whole thing works. Okay, so when you install the code and you run it on yourself, I mean, run it by yourself, you should be able to see something similar, and then you can try some of these things. Okay, so next week's class we will go into more details. Okay, I'll also release the next tutorial, and then we'll also go into more details about other mechanisms on how a task can talk to each other, send data to each other, and synchronize and so on. Okay, so I think that's all we have for today. If you have any questions, you can stay behind and ask me. Okay, if not, I'll see you all next week. Okay, the term paper, which part of the term paper you want me to, because we already went through the term paper the last lecture. So which part you don't understand? Okay, so late submission penalty, yeah, I haven't finalized that, but I mean, it won't be so bad. I mean, I think as long as you try to submit, I think you should be fine. Okay, so for term paper, maybe I'll just quickly summarize again. Okay, term paper, basically you are dealing with the 18-bit instruction set. Okay, so all you need to do, okay, is actually very simple. Okay, it may look complicated, but actually very simple. We know that our MIPS is 32-bit instruction, and in the term paper, all we are doing is we are bringing it down to a new architecture, which is 18-bit. Okay, so what you need to do is we need to make sure that, not make sure, we need to figure out how we want to use these 18 bits. Okay, so in the MIPS, when we had 32 bits, we said that, okay, we have opcode for 6 bits, RS, RT, RD, 5 bits, 5 bits, 5 bits, and so on. So we broke it up in a particular way. Okay, now in this new architecture, we need to decide how many bits for opcode, how many bits for the registers, and so on. So again, any decision you make will have some other things to factor in. All right, if I say I want only 2 bits for my register, then I only have 4 registers. If I have 3 bits for register, then I 8 registers, and so on. So it all comes down to making your own choices and sort of justifying how or or what you want to do. Okay, so if I have opcode is 3 bits, function is 2 bits, yeah, 8 times 4, yeah, so you can have 32 different combinations. All right, yeah, I mean, you can decide how many instructions you want to support and how you want to design the whole system. Okay, so you need to I mean, you need to go through the document again, correct? You need to provide all the deliverables that is laid out in the term paper document. Okay, so in terms of the overall architecture design, what decisions you made, all right, then you need to provide the instructions that are supported. Okay, then you need to provide a sample code for that objective of computing the square. Okay, so you need to go through the term paper, all right? All the requirements are clearly explained inside the term paper. Okay, what you need to provide, what is the code, what is the design, everything. Okay, so it is not that complicated. Okay, so you don't need to think too much. Okay, so again, it all depends on your own decision. All right, so if you say that I want 2 bits for opcode, 2 bits for each of this thing, okay, that is your decision. Correct. If I say I want 3 bits, okay, then other for 3 registers and 3 bits here, so you have 12 bits, then you have another 4 bits. Okay, what you want to do, up to you. Correct. So you can decide whichever way you want. Correct. There is no right or wrong answer here. Okay, so as long as you make a decision, you explain your decision, and based on your processor, how will you write the code to fulfill those the requirements there. Okay, so as long as you know what you're doing and how you're going to do it step by step, I think then it's fine. Oh, yeah, wait, okay, I wasn't sharing the screen just now. Yeah, so this is what I was. Yeah, so the MIPS is originally 32-bit, correct, and then you break it down into 18-bit. So out of the 18-bit, okay, if you decide different register to different bits, then your architecture will also change, correct? Because then you need to, I mean, generally the number of bits you use for registers has to be consistent, because the number of bits will be used to decide which register you support and which register you want to read from or write to. So register bits should be the same. Okay, so are there any other questions? Okay, so you don't need to worry about the registers reserved for the pointers and other things. Okay, so you just need to focus on the registers. You need to do the basic programming only for the requirements. Okay, so if no other questions, thank you. I will see you all next week. Okay, bye.